All right, thank you all for joining the sixth USPA technical training webinar. And my name is Ming Xiao, a faculty member at Penn State in civil engineering and the current president of the U.S. Permafrost Association. Well, today we have the great pleasure of welcoming Dr. Julie Malenfant-Lepage to give us a talk on the impact of water on permafrost and design of drainage systems for transportation infrastructure in permafrost regions. First of all, I'd like to give a quick introduction, and then we'll move on with the webinar. Well, the webinar series of the USPA is sponsored by Arctic Foundations, Shannon and Wilson, P&D Engineers, Geo Watershed Scientific, BD Stream, and a personal sponsor of Catherine Schneider. Today we have the great pleasure of having Dr. Julie Lepage from Norwegian University of Science and Technology. And Dr. Julie Lepage and obtained her master's and doctoral degree in civil engineering from Université Laval in Quebec City, Canada. Her research in the Arctic engineering has focused on the mitigation techniques to reduce permafrost degradation beneath a transportation infrastructure and on the design of road drainage systems, limiting convection and erosion in permafrost regions. Dr. Lepage is now a postdoc fellow in the Smarter Maintenance Road Infrastructure Research Program at the Norwegian University of Science and Technology in Norway. So and the format of today's webinar is as before, and we'll have about 45 minutes for the webinar. And then after that, we'll have about 10 minutes for question and answers. So during the webinar, feel free to type your questions by clicking the Q&A button, and you can type that. And then after Julie's webinar, and then she can answer the questions. So with that, I'm going to exit screen share. Okay, Julie, go ahead.
Thanks for the introduction. So we'll start sharing my screen. Here, share. And then I'm starting my presentation. Do you see it?
Yes.
Yes, okay, perfect. So let's start. We'll just reorganize this. So hi everyone, my presentation today will mainly focus on the research results that I obtained as part of my doctoral studies at Laval University in Quebec, Canada. So the title of my presentation is Impact of Water on Permafrost and Design of Drainage System for Transportation Infrastructures in Permafrost region. So the plan of the webinar today, I'll first start by addressing the issues of drainage in permafrost regions. I'll present the objective and hypothesis of my PhD project. Subsequently, I'll provide an overview of the study sites I had for the research and the main results I obtained for each of these. I will show you the results I obtained in regards of erosion and advection. And when I refer to advection, it means specifically the process to which heat is transported horizontally from by a fluid from one location to the other. And I'll discuss the progress made during my research and conclude by giving a few recommendations for future research and for the engineering practice. Significant water-related problems around transportation infrastructures have been widely observed across Canada and the rest of the Arctic for several decades. But the warming and extent of damage caused by water flow have long been underestimated in permafrost engineering. So I'll give here some examples of significant problems observed along roads and airstrips in the north. So we often see water accumulation at the base of embankments in the north. This is a picture of one of the airstrip in Nunavik, north of Quebec in Canada. We see ruptures of culvert and failure of the drainage system. This is a picture taken along taken in Alaska, actually. We also see a lot of sediments perpendicular to the roads, which are linked to water flowing under the embankment. And I don't know, I've been driving several times the Alaska Highway that drives through the Yukon territory towards the Alaska, and I've seen very often towing on the roads that are diagonal, and sometimes they have a little curve, and you don't really think they might be related because you don't see water. But once you go on Google and you have a view from above, sometimes it's very obvious. There's a lot of ponding, a lot of water in the area. So then it really helps to observe, to kind of see, okay, there is water flowing in that direction, and that could be the cause of the sediments we have been observing. In this photo, we see an important thermal erosion event which occurred in the spring of 1988 during the construction of the access road to the Salluit airport. So what happened, the concentrated flow at the outlet of one of the culverts caused a 2-meter depth gully. Here we see a significant depression at the toe of the Dexter Highway in the Yukon territory in Canada, and this depression is caused by groundwater flow and is recurrent. So they keep filling it, and it's always coming back. And this photo shows a major thermal erosion event which occurred very quickly within a month, following the rupture of an aqueduct in northern Russia close to a road. So it really shows how quickly thermal erosion can be. And as you can see, all these problems are likely to reduce significantly the lifespan of transportation infrastructures and safety for road users. What is important to know is that the current drainage methods are limited to a set of recommendations to avoid excessive permafrost degradation. And we can divide it into 2 main categories. So we have the method with low impact on permafrost. So we're trying to limit the heat transfer between water and the underlying ground, for instance. There are many recommendations in the literature for culverts. The picture here is used mainly in the Yukon territory, in the western part of Canada, where they put an insulation around the culverts to prevent heat transfer from water flowing in the underlying ground. And other methods, parts of this category, are the use of small bridges for crossing roads and the permeable embankments. The other category is include all the method with control impact. So we know that we will have permafrost degradation, but we make sure it occurs as far as possible from the embankment to keep the integrity of our infrastructures. So we have, for example, the recommendation of building the ditch as far as possible from the embankment. There is a recommendation at the moment in the literature of 10 meters. We have in this category water diversion channel, diversion berms, addition of water ponding in areas of the drainage system to reduce thermal erosion. This is a method that has been used in China. So they did implement drainage ditch perpendicular to the embankment to drain stagnant water at the embankment too. But it's important to know that we don't know the thermal benefits of any of these methods. So they haven't been investigated up to now. So the expertise that has been developed in Canada is very local and differ from one region to the other. And there are very few design criteria that do exist at the moment. So there is a great need to improve knowledge on the key role of water flow and heat transfer to frozen soils, and on the performance of road drainage system in permafrost regions. The main objective of my PhD was to develop new strategies for the design of drainage system to mitigate permafrost degradation issues resulting from water flow. And we had 3 research hypotheses for my research. So the first one is, can the Peclet number adapted to soil proposed by Kane and its collaborator in 2001 be used to quantify the risk of permafrost degradation around and under transport infrastructures, and therefore as a design parameter, since we don't have a design parameter at the moment. The second one was, can the critical shear stress obtained by the erosion device CSM, and the approach proposed by Grabowski and its collaboration in 2010 be adapted to frozen soils? And the last one, is there a correlation between the water flow in a stream or a ditch and the thaw depth? Following the hypothesis, we had 4 specific objectives, which are the following. The first one is to develop a method to calculate the maximum allowable flow, controlling thermal erosion in drainage ditches as a function of the critical shear stress. You have sketch of a drainage ditch on the right, and you see exactly where each of the specific objective applies. So in this one, it will be at the bottom of a drainage ditch. For the second objective, I had to develop a method to limit heat advection caused by subsurface flow along and under transportation infrastructures based on the Peclet number. The number 3, to develop an allowable flow criterion based on a relationship between water flow in a ditch and thaw depth. And the last one was to develop a relationship between the thickness of the active layer and the temperature at 30 centimeter depth. Regarding the field work, the main goal was to really improve knowledge on the thermal impact of water flow in natural conditions at the beginning and on the performance of transportation infrastructures in permafrost areas. So we selected 3 test sites across the Arctic as part of this research, where the ground is known to be sensible to permafrost degradation and thermal erosion. So the first test site is in Ilulissat, Greenland. And then I had another test site in Salluit, which is in the northern tip of the Quebec province in Canada. And if we travel to the west of Canada, I had a test site that is really at the border between Alaska and Canada. And you see here also the Beaver Creek test site, since I've been using the data from this test site for the validation of my results. All the 3 test sites are characterized by fine grain and ice-rich permafrost having a 0 annual amplitude near -3 degrees Celsius. The first site, which is in Ilulissat, Greenland, the main goal was to study the vertical and horizontal extent of permafrost degradation caused by water flowing and ponding. Let's see. So I took a lot of surface measurements at the test site, such as thaw depths, temperature in shallow boreholes, soil temperature at 30 centimeter depths along the profile, stream flow, water temperature, as well as water content of the active layer and permafrost. So here you see the profiles that were done across the stream and across the 2 ponds. And this site was chosen specifically for this research because of the small, well-defined catchment area. So it's very small and there's no trees as well. So it was really easy to see water flowing at the surface. And also because of the possibility of comparing the results obtained with previous intensive studies carried out in Ilulissat between 1978 and 1985 in connection with the airport construction. So we have a lot of data in this area. And the Technical University of Denmark has also done in the past years automated ERT survey south of the airport. So they have surveyed through a whole year. And finally, the test site is characterized by the presence of many water tracks and a lot of mud boils as well. So in the next slide, I'll show the results of survey line 3 here across the stream. The first graph, you have the elevation profile. The stream is in the middle, and here you have the depth of frozen ground that was probed at every meter. The graph below shows the temperature at 30 centimeters depth at every meter. Here you have the active layer thickness, And beneath, you will see the both ERT profiles that we obtained with the gradient and the dipole-dipole array configurations. So it was estimated at the site that a good value between the unfrozen and frozen ground was around 500 ohm meters. So which is represented, which is the limit between the yellow and the brown color on my graph. So you see clearly here that that it is unfrozen below the stream at that location, but it was not on all, it was not unfrozen to the bottom for all the different profiles. So the main results I obtained is that permafrost degradation due to the presence of water occurs mainly vertically. So it was really interesting to see at the site that I was probing permafrost just by the stream, and it was very, very close to the surface. The soil temperature at 30 centimeters depth increases sharply in the venicity of the watercourse and is linearly correlated to the thaw depth. The thaw depths under the water tracks are 1.5 to 2 meters to 2 times deeper. And we observe a large increase in resistivity around -1 degree Celsius at the site, and not necessarily between the limit between frozen and unfrozen ground. The second test site is located along the Alaska Highway, very close to the border with Alaska. And the main goal of this test site was to evaluate the performance of a newly constructed rectangular ditch located 10 meters from the embankment near the Yukon-Alaska border. So it's very common in this area to build rectangular ditches. And we expect that permafrost will be degrading. So we kind of put it at a certain distance from the embankment. And then once the permafrost is degrading, then at some point the vegetation cover will fall over the slopes and protect permafrost again, and we will reach stabilizations. So I did a lot of surface measurements as well at this test site. Same thing, a lot of ERT surveys across the ditch, along the ditch. And we have boreholes from the Yukon Research Center. There's one in the ditch. There's one in the natural ground at the bottom of the climate station you'll see on the pictures. And now there's one that was added between the ditch and in the zone between the ditch and the road. So it was added last year. We did also flow rate measurement in culverts during the research, and the ditch has been mapped every year, either with a DGPS, high precision, zip level, and we have also LIDAR data that are available at the test site. And it is a site that contains a large network of ice wedges that are estimated to be over 10 meters deep. The figure you see compare all the elevation profile taken between 2015 and 2017 with the cross-sectional area of soil excavated during the ditch in 2013. So this is the square you see on the figure. And if we look at the results, the permafrost thawed very rapidly at the test site in the interceptor ditch during the first 3 years after construction, but the ditch appeared to have stabilized thereafter on the short term. We have now the elevation data for last summer, so I will then be able to see if the ditch is still stabilized on long term, so after 10 years. But in the first 3 years, it did really seems to have stabilized. The ditch from 2013 to 2016, the ditch has deepened by 0.8 meter, and the cross-sectional area of the ditch is 1.8 times larger. Rectangular ditches do collect snow in winter, which inhibits ground cooling. So we see that with the borehole that is located in the ditch. Permafrost, it's quite cold in this area, so it's close to -3. So then we have to be very careful if we do those ditch in very warm permafrost. The drainage slope of the new ditch may become inadequate after 2 years of operation, because after construction, there was a lot of permafrost degradation that was filled with water. So the drainage can become inefficient very rapidly. So it's very important that we maintain those ditches regularly until we reach the stabilization. Following the excavation of the ditch, there was a waterfall that was created and led to the formation of a thermal erosion gully. The retreat rate that we measure was 23.6 meters per year, which is very significant between 2013 and 2017. And it has a depth of 2.8 meters. And the thermal erosion developed into a thermocast. So I'll show you some picture here. So you have the fall that was created just after the ditch was excavated, because there was a small stream coming perpendicularly to the ditch. And then in April 2015, when we went at the site, we observed that the ground was cracked on the surface and that the stream was now flowing on the ground. So water probably infiltrated into a sinkhole, and the melting of an ice wedge and an underground tunnel developed. And 4 months later, in September 2015, the tunnel ceiling had collapsed and a pond had developed at this location. So the degradation of permafrost has progressed in the following years and led to the development of a thermocast. And now the water regime in the ditch has changed, because now water accumulates in the thermocast and flows in the ditch only when full. And here you see a picture of, it's in one of the section of the ditch. The ditch is 500 meters long, so it's quite long. What happened exactly is there is at a few locations the ice wedges that melt and release a lot of sediments into the ditch and completely obstruct the drainage. So at this location, water has been ponding since the beginning. So it's a very big pond of several meters. We tried to drain it, but it was not successful. So the water has been standing there since then. And what we observe is that the thaw depth under the water accumulation zone in the ditch is 1.3 times greater in comparison with areas where there's no water ponding. And the water temperature was 1.5 times warmer than running water in the ditch in August. The last site is in Salluit, which is in Nunavik, northern Quebec in Canada. At this site, the main objective was to evaluate the performance of a new shallow drainage ditch with riprap placed at the embankment toe. The ditch is located upstream of the road, and downstream you see here chimneys. So it's a e-drain that has been implemented. So it's a mitigation technique. How it works, there is a drainage membrane that is implemented in the slopes and that are connected to inlet chimneys and outlet chimneys. So in the winter, when ground cools, then the heat is going through the drainage layer and is expelled out through the chimney. So it helps to cool the ground. At this site, I did the same, a lot of surface measurements, ERT surveys. There's also a fiber optic cable that runs on both sides of the roads, taking measurements regularly every 25 meters. We have also 10 thermistor cables into the road, and we have also 3 inclinometers. So when I was at the site, I investigate the drainage, and I had a look at all the culverts. And then unfortunately, even after the implementation of the newly drainage ditch, I observed that many of the culverts were either placed too high or either the ground has settled in front of them, so water was not flowing through them, but underneath the road. I observe as well in one places that water was directly flowing out of the embankment, and in many places the embankment was wet at the bottom. So it's it's not easy to do drainage, and definitely in permafrost area, the water doesn't go where we want it to go. And all the orange lines are where I did some ERT surveys. I will talk about it a little bit later. The thermistor cables incorporated into the airport access road in Salluit in 2012 made it possible to measure the effect of water flow underneath the road embankment, a phenomenon that is rarely captured. So we did measure a warming of 1.9 degrees Celsius at 1 meter depth on the annual maximum temperature curve that you see on the right. The borehole is located upstream of the road at the embankment toe. And if you look here, you see kind of a wave in the profile. So this is linked to water flow at the test site. So you really have to be keep an eye on those wavy profile in your data. So it might be related to water. And what we observe as well, if you look on the ground thermal regime at the bottom, is that the ground thawed 33 days earlier at 1 meter depth than the ground above at a depth of 50 centimeters. We also found out that water not only accelerates thaw settlements under the road, but its presence can cause significant frost heave. I'll show you a picture that is quite relevant. First, when I visited the test site, and I've seen this huge crack along the road, so we were really sure that permafrost was degrading in the embankment slope, even if there was a e-drain that was implemented. But after investigation and analyzes the data from the inclinometer, the team at Université Laval found out that permafrost was not degrading at all, but it was really the movement of frost heave due to water flowing under the road. So when in the winter, when you have freezing, then the slope lift, and then it kind of slide down in the summer during the warm period. And then as a conclusion, we add that the e-drain can limit permafrost degradation even if there are water flows under the road. And ERT identifies thaw-sensitive areas along the road. So I strongly recommend to use it if you have any drainage work to do along your infrastructures. It's very important to know which zones are very close to thawing. Usually if you take temperature measurements, you don't really know how close the ground is to thawing, but with ERT surveys, since it's very sensible to unfrozen water content, you can really see, okay, that zone, I really need to be careful and make sure water won't be concentrated or ponding into this area. So ERT can be a very useful tool for this. Regarding the result for the erosion tests, it's important to be aware that sediment motion initiation has been widely studied for over a century, but the erodibility potential of frozen soil is still poorly understood and has been less documented in the literature. So during my PhD, I did some erosion tests to determine the critical shear stress for a frozen silt, which is the type of soil considered to be the most sensitive to erosion. The critical shear stress is an important erosion parameter and is defined as the pressure generated by water on the soil surface when erosion is initiated. For my research, I've been using an erosion device called the cohesive shear strand meter that I've been developed in the UK. I did this experiments in the lab at the Norwegian University of Science and Technology in Trondheim. There was a great need in the marine research group here at NTNU to obtain cohesive shear stress values for the Arctic coastal erosion models. So then we collaborate together on this project. I also brought the cohesive strand meter at my test site, and I did some in situ measurements. Why there's a lot of erosion device, and why we decided exactly to choose that one. It's because it's very light, it's portable, so easy to transport into the field. And the tests are very easy and done in less than 2 minutes, for example. So I will present the device quickly. So here you have the operation channel. You have a water reservoir, which is connected to an air cylinder for pressure. And then water is sent through the cable here, through the sensor head, which is inserted into the soil surface. And if you look into the sensor head, there is a light transmitter and receiver, and here you see the jet nozzle where water is fires. How does it work? The erosion threshold has been determined by the manufacturer. So when, let's say, when you measure a decrease of 10% of light transmission in the sensor head, that's when we say that we have erosion. So that's when the erosion is initiated. And all the soil samples that have been that I tested in the lab, they were saturated, and there was with no excess water content. And then there's some processes to do with the data coming from the cohesive strand meter. So I followed the methodology proposed by Grabowski and its collaborator. So once you need, it's very important that you transpose the pressure measure inside the sensor head into a pressure at the soil surface. So I've been using the methodology from Vardy and its collaborator in 2017. So then I calibrate my device into the lab, and I obtain my own equation of P stag, mean pressure at the soil surface. And then once you have this, then you need to transpose this vertical pressure into an horizontal pressure. So I did use the equation developed in the laboratory by Grabowski and its collaborator. And then once you have the horizontal pressure, then you obtain the critical shear stress. So what they did in the lab, they tested different soil sample mixtures and with a flume and a cohesive strand meter. And that's how they obtained the collaboration between the two devices. If we look at the data I obtained in the lab, so it's important to say as well that I use a water temperature at +2 degrees Celsius for my tests. On the graph here, you have the temperature and you have the critical shear stress. So for temperature below -2 degrees Celsius, the critical shear stress at which soil particles will be removed is temperature dependent. So the cohesive shear stress of the silt tested increased by a factor of 1.6 for every degree Celsius decrease between -2 and -6. But if you look at the data for the partially frozen ground between -0 and -2, and for the unfrozen ground samples, the average are very similar. So I obtained a value of 0.28 Pascal for partially frozen and 0.27 Pascal for unfrozen ground. So it is generally believed that frozen ground cannot be easily eroded since ice is bonding soil grains together and increasing strength of the soil when the ground is frozen. However, the results we have in this study show that this bonding starts to be effective against erosion only at -2 degrees Celsius for a saturated frozen silt. So, but it's very important to be aware that if we test different type of soils or clays, for example, probably we need to expect that this relation can be different depending on the unfrozen water content. And yeah, to prevent and control soil erosion during the construction of drainage ditches in permafrost environment, an approach during the study was to develop, it was to access the maximum water flow that can be concentrated in an open channel as a function of the critical shear stress. So I did use two well-known equation in hydrology, the Manning equation and the equation of Dubois. So I combine them to obtain this equation of the flow limiting erosion according to the critical shear stress here. D is related to the depth of water in the ditch, W is the width, N is the Manning roughness coefficient, S is the drainage slope, and here you have the density of water and the gravity. So the critical shear stress is the solely parameter considering the soil properties in the equation. So it will consider soil type, water or ice content, soil temperature, and well bulk density. I did validate the equation with the data from the Yukon test site. So here an example I made. So you have the flow here in cubic meter per second, and at the bottom it's different different events in 2015 and 2017. In blue, you have the flow measure in the culvert at the test site, and in orange is the flow limiting erosion that have been calculated with the equation. So I had a look at the two most important rain events at the test site, and I had a look at the 3 days before when on 2 days where there was no rain recorded to have a look at what was happening in the ditch. So if you look on May 25th, 2017, for the daily mean, we have a value of flow measure of 0.0007 cubic meter per second, and a flow limiting erosion of 0.003. So the flow measure is smaller than the flow limiting erosion, so no erosion should be expected at the test site. But if we look at the rain event, we add in the ditch water depth of 17.9 centimeter measure, which gives a flow measure of 0.06 and a flow limiting erosion of 0.02. So for this rain event, we expect that sediment have been mobilized. And in the culvert, we see there's a layer of sediment. So we know that at certain period, there is some erosion and sediments have been transported into the ditch. If we look at the following year, same thing, June 1st, no rain, no erosion. But we recorded a major change in the data. So on June 4th, we measure a flow of 0.46 cubic meter per second, which is approximately 11 times greater than the flow limiting erosion calculated at the test sites. So probably what is occurring at the test site now, 1 year before the thermocast developed, and then all the water coming from the snow melt accumulates in the thermocast, and then the small stream is flowing directly into the thermocast. So then water is accumulating at this location until it gets full, and then all the water is released very rapidly into the ditch. So that's probably why we measure such a high flow rate, but it means at the same time that more erosion are expected to occur at the test site in the following years. I just wanted to come back on the different heat transfer mechanisms. So the three main mechanisms of heat transfer are radiation, conduction, and convection. So very rapidly, times are flying. So here you have, so the convection is the process of heat transfer involving the movement of the fluid. And it is obtained by using the Newton laws of cooling, which look very simple. So the H is the coefficient of heat exchange by convection, and Ts, it's the temperature at the sole surface, and Tf, it's the temperature of the fluid. But however, there is a very high variability of the coefficient H. So it can vary between, for instance, 100 and 900 watt per square meter for degree Kelvin. So the equation is very difficult to use. And moreover, we don't know most of the time what is the temperature of the soles and what is the temperature of the fluid. So that's why the convection coefficient, that's why the equation of convective heat transfer has shown that dimensionless numbers are very useful to solve fluid mechanics and particularly convective problems. So that's one of the reasons why we wanted to adapt the Peclet number proposed by Ken in its collaboration for Arctic salts to groundwater that occur along transportation infrastructures built on permafrost. So this is the equation that has been proposed by Ken and its collaborator. So here you have the fluid density, the specific heat, the fluid velocity, the length over which heat transfer occur. And then this is a ratio if you're looking at heat transfer over a long distance. And here you have the thermal conductivity. If you have a Peclet number above 1, that means that convection is dominant. And if it's below 1, that means that convection is not significant and conduction is the main heat transfer mechanism. And then I rewrite the equation provided for two different situations to make it a little bit clearer. So this equation is for rain and snow infiltration. So what is different here? It's the speed of infiltration into the ground, and D is the depth of unfrozen soil where heat transfer occur. And for groundwater flow, then here you will have the hydraulic conductivity, and S is the slope of permafrost, because we made the hypothesis that the hydraulic gradient is probably equivalent to the slope of permafrost, or even the slope of the soil surface. And in an engineering context, the objective is really to adjust the parameter used in the design of drainage system to ensure that the Peclet number remains below 1. So it has been demonstrated by the University of Montreal that groundwater was crossing the road at the Beaver Creek experimental site caused the ground beneath the road to warm between 2 and 4 degrees Celsius. So I did use this test site to validate the data. The Peclet number has been calculated for 3 different situations. The first one is for initial conditions, so prior to the road construction. So I calculate the Peclet number when water was flowing over a distance of 20 meters. At the test sites, there is 0.4 meter thickness of peat over 0.3 meters of thawed silt, and the slope is 4.2%. So the Peclet number obtained is 0.34 for if water is flowing through the peat layer, and 0.04 if water is flowing through the silt layer. If we look at the second condition after road construction, so most of the time the thaw depth underneath the road will increase. So I did the same calculation for a thickness of 2 meters that was measure at the test site in Beaver Creek. So for the same, if I do the calculation again, I obtain a Peclet number of 0.08. So again, there is no convection occurring for this situation. But most of the time, once you have once you build a road, then permafrost will start thawing, and you will have depression that will form underneath the road, and this depression will be filled with embankment material having higher hydraulic conductivities. So I did this the calculation again for water flowing through a 2 meter thick layer of embankment material, and I obtained a Peclet number of 4.3. So which means that for this situation now we have a convection occurring at the test site, which occur at way faster rate than conduction. So we expect that the degradation accelerated at the test site. It was observed also during that research that rectangular ditches do stabilize as expected, but however, it's important to pay particular attention when there is a water course flowing into the ditch, and the initiation of the thermal erosion gully that developed at the Yukon test site can be explained with the Peclet number. So if you look at the graph on the right, you have the slope and then the Peclet number here. So the construction of the rectangular ditches changed drastically the natural flow slope. So we had a slope of 1% at the beginning, and it's changed to 90% locally. So you see that when we do that, the Peclet number increase, and then we have convection. And then with time, you get permafrost degradation, and then the slopes is lowering down. And so from the graph, you see as well that if the slope is getting less than 16%, but then convection should start to be less significant at this test site. The Peclet number also make it possible to determine the minimal distance required between the ditch and the embankment toe. So here is very quickly an example from the Yukon test site. So we have 3 locations for potential for a ditch, number 1, 2, and 3. This one is at the toe of the embankment, 2.75 meter, 475 meter. So I did calculate the Peclet number for all this situation. And I succeed to probe the top of permafrost in this location, but as you know, once you get close to the embankment, it's very hard to probe. The soil is very dense. There's a lot of granular material. So I did use the relation I've developed during the research, where I get the active layer thickness according to the temperature at 30 centimeter depth I measure. All the dots are related to the data I measure in the field in Ilulissat and in the Yukon. So I did measure the temperature at 30 centimeters depth here in the location, and then I obtained an estimation of the active layer for the calculation, from which I obtained a slope of 9%. So if you look at the results, so then we have a Peclet number of 1.69 here, number 2.31, and number 3.007. So probably the most optimal drainage ditch will be number 2, because we need to make sure the Peclet number is below 1. But we don't want to have the ditch too far away from the toe, so we want to make sure we don't have any water ponding and that is not drained as well. But we still need to determine which Peclet number will be optimal, or if it's between 0.1 and 0.5, for example. And I developed some design charts to limit advection based on the Peclet number. So very quickly, you choose the maximum thaw depth at your test site, the distance traveled by water, the slope of your test site, the hydraulic conductivity, the thermal conductivity, and then you obtain the Peclet number for your design. The research progress, we did improve knowledge on the key role of water flow and heat transfer to frozen ground, on thermal erosion, and on the performance of road drainage system built in permafrost zones. The critical shear stress of a frozen silt has been determined for the first time with an erosion device for different freezing temperature. And we did create the first design tool for road drainage in permafrost area that helps determine the ditch embankment distance and the dimensioning of drainage ditches. And I want to come back on the specific objective I presented at the beginning. So we succeed to answer to 3 of them, but not number 3, which was to develop a flow criterion based on a relationship between water flow in a ditch and thaw depth, because it is very hard to measure the flow rate at a test site. Sometimes we arrive at the test site, the water is flowing underneath culverts, or sometimes we measure the flow into the culverts, but it comes from 2 different directions. So we don't know, okay, do we have 75% of the flow from that direction? And then, so it has been definitely a challenge to measure flow rate in the field. So we really need to work on this aspect. And I have few conclusion and recommendation for future research. So we need more instrument at the sites. Definitely, the calibration equation proposed by Grabowski must be expanded to higher pressure because for now it's very limited. Further research with the cohesive strand meter device is needed on different salt type, ice content, water temperature. We need to determine soil hydraulic conductivities in the north. We don't have a lot of data on this. And we need as well to know the flow slopes around and other transportation infrastructures. We have very limited data on this. And that would be important to convert the Peclet number to heat flux. For engineering practice, we need to ensure that drainage is always optimal around infrastructures and that ditches are maintained in the years following the construction. The flow estimation for the northern watersheds must be improved because we have very little climate station at the moment in the north. The addition of a drainage category for the mitigation technique will be very important. So we really need to make sure we do understand all the techniques that are implemented for drainage, because if we implemented a quite expensive mitigation technique to cool the ground, if we don't control the water, then it can definitely limit significantly the benefit of the mitigation technique implemented. And finally, water management. I would like to conclude with this. In permafrost region is really a challenge, and it requires knowledge from a lot of disciplines. So I really believe that that we will move forward to multidisciplinary research with multidisciplinary research themes. Thanks everyone for listening my presentation today. I'll be in Whitehorse next week. I will have a poster on Thursday. So if you're there, please, if you have questions, you can come and talk to me. That will be a pleasure. Stop sharing.
Thank you. Thank you, Dr. Lepage.
Thanks.
So we have some time. And feel free to type in your questions if you have any. So far, we have a couple of questions. If you, Dr. Lepage, if you look at the Q&A and see if you can answer.
Yes. Okay, from Charlie, although your work consider a drainage ditch, relatively shallow depth of permafrost, would your work be applicable to deeper permafrost layer when permafrost groundwater or enter? Yes, yes, it does. I kind of adapted the equation. I don't refer to active layer only to active layer thickness, but to maximum thaw depth, which does include the active layer and the thaw lick that are very often present in Arctic. So yes, it's possible to use it for that. The Salluit frost heave is fascinating. Do you know the gradation of the material that the heaving embankment was constructed from? Was there a significant clay component? Thank you, great presentation. Yes, there is a significant clay component. It's a silt, but there is a significant clay component at the sites. And there's few, if you want to know specifically for the material, there's few reports that have been published by Université Laval on this that you can find online. And how did you take into account the change of ice content with it?
Julie, if you could maybe read out the question. I'm not sure if in the recording, the questions will be showing on the screen. If you could read out the question and answer that, and that would be great for people later on to watch it. Thank you.
Okay. So I have a question from Kevin. So how did you take into account the change of ice content with vertical and lateral extent in determining erosion parameters? Erosion parameters. So far, I've been testing mainly in the lab with a silt, which was saturated. So I did not do any experiment in the lab with excessive ice content. So this has to be done. So this is for future research. Will this be developed in another question? Great information. Will this be developed into an applied manual like the old Canadian permafrost design material? Hopefully in the future, but the tools that were created needs to be tested in more field test sites. So yeah, so feel free to use them and then give me some feedback as well on this.
Dr. Lepage,
Yeah.
what for site 2 and the ditch beside the road, it seems like there's no surface protection of the ditch after construction. Do you
Yeah.
think there's any surface protection such as gravels, a layer of gravel would reduce the permafrost degradation?
Yes, so what they did actually for the ditch, now there is a very thick vegetation cover that has regrown. So in areas where vegetation can grow rapidly, that's one of the techniques that you can use. So after a few years, but now there is a lot. I was surprised how quickly the vegetation came back, and now it definitely stabilized the soils. But if you're in an area where growing is very slow, yes, definitely to add some granular material or a blanket at the bottom as well would help.
Thank you. And for site 3, you also mentioned the fiber optic cable. What
Yeah,
does that measure?
it measures temperatures.
Okay.
Yeah, yeah, continuously. Yeah. So more results on this coming as well.
Okay. Great. We're almost at 2 o'clock Eastern time. I don't see any other questions. Great. Okay. Great. Okay. Thank you. Thank you, Dr.
Yeah,
Lapage, and
you're
for the great
welcome.
presentation. And thank
Thank
you
you.
all for audience to attend. And after this, and the PowerPoint presentation of Dr. Julia Lapage's talk will be shared with our audience.
Yes, I will. Yeah.
Great. That's
Thanks.
all.
Have a nice day.
Thank you. Thank you so much.
Yeah.
Okay, bye-bye.
Bye.